Hey, let's do more examples. This one's a little more in depth, and we're going to need to use what we've learned in the past sections. And we kind of just tie it all together. Then you'll be done with the videos for at least raising stuff to powers, and then we'll jump into those roots. There's your theorem again, Old-Demois. And this time we're going to look at using Demois' theorem to find -5 plus 5i raised to the fourth power. And we're going to leave our solution in the standard form. This is how I'll ask you on your final. This will be, I'm going to say leave your solution in standard form. So let's stay in practice. In your homework, you might get rounded decimals, but I like to make them work out to where it's going to be one of those common ratios that we mess around with so much. So let us go get it. Now, what makes this problem a little bit worse than the others is this isn't in trig form, which means we need to take it and put it into trigonometric form. That's what we learned how to do in our past sections. So that is one of our first steps. Therefore, let's go. Let's go. All right. So what do we have here? So let's just call Z. Let's take everything that's inside, not to the fourth power, just the stuff that's inside, and say that Z is equal to -5 plus 5i. And we'll convert it into our trigonometric form as we've done before, and then we'll raise that thing up to the fourth power. So let's just make a little line here. And what's the game? We got to get the radius, and we got to get the angle. Radius, no big deal. Let's go get it. So the radius, actually, I'm going to do this in blue. Who cares? Who cares? Let's just go. The radius is equal to the square root of our two components added up, or squared and added up. So we pop in our -5 and our +5. What do we have here? That's going to be, what, 25 plus 25? Right, 2/4 gives you 50 cents. And then let's break this thing down, huh? 2/4, right? So root 25 times root 2, right? Just using that rule. And then we have 5 root 2. Cool, we got a radius. Right? Radius is never too big of a deal. Have you started to catch the pattern yet? That when they're the same number, I know that they're different signs, but when they're the same numbers, it's always going to be that number times root 2, the positive of it. No, patterns are dope. Makes things go quicker. But let's continue on. Now, the trickier part is we're going to have to go find that angle. So before we do, let's just do something real simple. Just make a little plus sign. You know your XY graph? So we're going to look and go, all right, so we have a -x, or a negative real portion, huh? And we have a positive y, the imaginary portion. That means we'd be in quadrant 2, huh? Isn't that where x's are negative, y's are positive? That's your real, this is your imaginary, but come on, man. The real's like your x's, the imaginaries are like your y. So we're in the second quadrant, meaning we're somewhere between pi/2 and pi. All right. Now that we know that, now we can go and mess around with our formula, because there is a little bit of thought that goes into it depending upon which quadrant. So we can say right away that we'll use the tangent formula here. So let me change my color and go the tangent of the angle we're looking for is just equal to the y/x, or the the imaginary portion over the real portion. But that's +5 over -5. So that tells us that tangent of theta is equal to -1. Now, if we didn't make our little XY graph, or our real imaginary graph, and know that we're in quadrant 2, if we just hit this with an inverse, we're going to get the wrong quadrant. All right, there's that extra game where we're going to need to add pi to it, or just use some logic. So while I look at this and I go tangent of theta equals -1, and I want to know like what angle it is, I already know it's in between pi/2 and pi. And I know it's some multiple of pi/4. It's freaking 3 pi/4 just by looking at the thing. But hey, let's just go. So let's take an inverse on both sides, giving us that theta is equal to inverse tangent of -1. And if we weren't looking and knowing what's going on, when we punch that thing into a calculator, you're going to get -pi/4. But that's not the answer, right? -pi/4 is down here in the fourth quadrant. That's absolutely pi away. You'd have to add pi to it in order to get it to go around. So since we are in the second quadrant, anytime you're in the second or the third, you're going to need to add pi. So once we add pi, we end up with 3pi/4. That makes a heck of a lot more sense than -pi/4. So be very, very careful when finding that angle. All right. We've done the hard work. Now we can put this into our trigonometric form. So on the left-hand side, let's begin writing again. So our radius we found to be, what was that? 5√2 times cosine of our angle is 3pi/4 plus I sine of 3pi/4. Cool. Well, we're done with everything on the right-hand side. Let's just start to zoom in a little bit on the left. Now, we need to take this and raise it to the, what was that, the fourth power? Yeah, we got to raise it to the fourth power. So now let's use Demoise. Right down here, we're going to say, let's find our answer. We're going to raise this thing up to the fourth power. So we're going to take this whole thing, our 5√2 times cosine of 3pi/4 plus I sine of 3pi/4. Whew, that's a lot. And we'll raise it up to the fourth power. Cool. Let's get it. Let's get it. Let's get it. Okay. So let's put our equal sign in here. So we're going to take our radius, our 5√2, and we're going to raise that thing up to the fourth power. Next, we're going to need to multiply our angles by that 4. Look how convenient this is too, huh? Look how frigging convenient this one turns out to be. You're going to multiply by 4, and there's already a 4 in the denominator. Oh, that's nice. So that means the 4s are just going to cancel out, and we just have to take our 5 to the fourth power, or 5√2 to the fourth power. Look at this, pulling out a calculator. I'm like, I don't want to try to do this in my head, even though you should be able to. Raise it up to the fourth power, and we get 2,500. So you get 2,500 times cosine of 3pi plus I sine of 3pi. Well, 3pi is the same thing as pi, right? You just take away 2pi. So when we go to evaluate this, we have 2,500 times cosine of 3pi, which is the same thing as cosine of pi, which is equal to -1. Sine of any multiple of pi is always equal to 0. So this is just going to be no friggin' i's, none of them. So once we multiply these two things together, we get -2,500. And that, my friends, is the solution. We evaluated it. We got it all the way down to standard form, and turned out it was a real number. It's also a complex number. So that was our game. Fun stuff, huh? Fun stuff. So we're utilizing what we used before and then using just another step. And I think the Demoise theorem is actually some of the simplest parts of this whole problem. It's all the stuff we learned before. Next, we're going into roots. They're a little more challenging and they're a little more tedious. So we'll have a couple more videos on those, and then we'll wrap up our section on complex numbers. We'll be done with chapter 4. We'll move to chapter 6. We skip over 5. All right. I'll see you in the next video.